Okay, let's continue our discussion about hypothesis testing. The first thing we're going to do is just look in a little more detail about type 1 and type 2 errors. Then I'm going to talk to you about p-values, really important concept, in fact one I use a lot. And then I'm going to do just a couple example hypothesis tests for you. So let's consider this example where we have steel bars that come in, and we expect the mean tensile strength of these bars to be 10,000 pounds per square inch with a standard deviation of 400 pounds per square inch. So what we want to do is we want to take from that shipment a sample of 100, calculate the average tensile strength of that sample of 100, and if that tensile strength is too far away from 10,000, we want to reject that shipment and send it back. We decided in this hypothesis test to use a level of significance of 5%, which, if you recall, means that we want there to be less than 5% risk that if the mean is the mean tensile strength, if the mean tensile strength is really 10,000, we want the chance of incorrectly saying that it's not 10,000. We want that to be 5% or less. So based on the 5% level, and I'll show you how we get these later, it turns out that if the tensile strength is less than 9,922 pounds per square inch or greater than 10,078 pounds per square inch, then we're going to send the lot back. If it's between those two numbers, we're going to keep the lot and assume it's okay. So let's talk about a type 1 error first. A type 1 error would occur if we happen to get a sample whose sample tensile strength, whose average tensile strength was more than 10,078 pounds per square inch or less than 9,922 pounds per square inch. These values, this 10,078 and 9,922, are actually calculated based on the level of significance to 0.05. If we change that level of significance, these values would change. So effectively what's happening here is that only 2.5% of the samples would have a sample mean greater than 10,078 if the real mean is 10,000, and only 2.5% of all the possible samples would have a sample mean less than 9,922 if the real mean is 10,000. So there'd be a 2.5% chance that we would pick a sample whose tensile strength is too high, a 2.5% chance that we'd pick a sample whose tensile strength was too small if the mean was 10,000. So there's basically a 5% chance that we would go into that population and pick a sample that would tell us to reject the lot when in fact we should have accepted the lot. And that would be a type 1 error. And again, these values, this 1.96 and minus 1.96, are determined by the level of significance that we selected. Now the type 2 error is a little different situation. It's a little tougher because when you talk about a type 2 error, what you're talking about is the chance that you will not reject the null hypothesis when in fact it's false. So what's the chances that we conclude that the mean is 10,000, or we're not able to reject the fact that it's 10,000 if it's not 10,000? So we're looking at a picture here where we're actually looking at the case where the actual mean is 9,900, and yet 29% of the samples would have a tensile strength greater than 9,922 and would therefore fall into the acceptance range for the hypothesis test, testing the hypothesis that it's equal to 10,000. So this would be the case. There would be a 29% chance that we would conclude the mean is 10,000 when in fact it's not. Now, what would happen if the mean was 9,800? Well, in that case, this curve would move over and that chance of a type 2 error would diminish. And in fact, if we moved it over far enough, if the real population mean was far enough away from 10,000, there would be little to no risk of incorrectly concluding that it is 10,000. The problem with a type 2 error in calculating a type 2 error is that to do that calculation, you need to know what the real population mean is. Well, we're never going to know that. If we knew what the real population mean were, we wouldn't be doing the hypothesis test to begin with. So the best you can do in terms of finding the probability of a type 2 error is do a what-if scenario. What if the mean is 9,900? What's the chances that we conclude that it's 10,000? What if it's 9,600? What are the chances we conclude it's 10,000? What if it's 11,000? What are the chances we conclude it's 10,000? So that's the best you can do because we don't know what the mean is. So the best we can do is say, what if it's such and such? Then we can calculate the probability. So type 2 errors are a little more difficult to deal with. Not harder to understand, but a little more difficult to calculate. Okay, let's talk for a minute about a p-value. We've got a definition up here for a p-value, and this definition is accurate, but I'm going to give you a little different definition, then I'll come back to this. What the p-value is the actual probability of incorrectly accepting. If you remember when we start the hypothesis test, we set a level or a value for alpha, which is the risk of incorrectly accepting that we're willing to take. P is the real probability of incorrectly accepting. So of course, if P is smaller than alpha, then the risk is less than what you said you were willing to accept, and you would reject the null hypothesis. If P were bigger than alpha, you would not reject the null hypothesis. Let's just take a look at this definition for a second. P is the probability of observing a sample value as extreme as or more extreme than the value observed, that the value observed being the test statistic, given that the null hypothesis is true. So what's the chances that you could get the value of the test statistic if that null hypothesis is true? And that value would be the actual probability of a type 1 error. And I'm going to show you an example of that in just a minute. Maybe a little easier to understand at that point in time. Okay, let's take a look at an example here. We have a recovery room at a hospital that's recently been enlarged, and what we believe is that the average number of patients that are accommodated in a day have now increased to the point where it's more than 25. More than 25. More than means greater than. Greater than does not include the equal mark, and therefore the greater than will be the alternate hypothesis. Less than or equal to will be the null hypothesis. The data is given to us here. These are the 15 values that 15 days that we collected the data, and we're going to use a level of significance of 0.01. We are assuming that the population from which we're extracting the sample is normal. And if you recall, in our last video, we talked about two different possible test statistics if you take a sample on a single population and want to test a hypothesis on the mean. One was the Z and one was the T. The Z calculation was appropriate if you knew the population standard deviation. The T was appropriate if you did not. In this case, we do not have the population standard deviation. We don't have anything more than the sample data. So this is all we know. Okay, now I've gone to Excel here, and I've got the data that we just saw in the PowerPoint slide over here in column A. I've written the hypothesis based on our previous discussion. We want the alternate to be greater than because the wording said more than, and the equal must be in the null. The level of significance is 0.01, and since we are testing a single population and we're looking to test a hypothesis on the mean of a single population, there are only two possible test statistics, and they've been previously discussed. The standard normal Z, and the T. This case, we're going to use a T distribution because the population standard deviation is not known. This is the test statistic. We could go over to this data and calculate X bar and calculate S, and we know that N is 15, and we could do this, but I'm going to let Excel give me a little bit of help on this. I'm going to use something. I'm going to go up here to data, and I'm going to go over to the right and select data analysis. Now, data analysis is an add-in. If you select data and you don't see data analysis, you need to go back to your add-ins and add data analysis in as an add-in. Okay, so I'm going to select data analysis. And under data analysis, I have several options. The option that I'm going to select is descriptive statistics. I'm going to hit OK. And the first thing it asks me for is what is the data that you want the statistics on? And of course, that's the number of patients per day. I did include a label in the first row. Now this is something funny here. I don't know why Excel does this, but when I click on output range, for some reason the cursor jumps back up to the input range. I don't know why, so I have to manually go down and click on the output range area and then select a location for the output, and then I want the summary statistics, and when I hit OK, it gives me lots of information here, right? For example, here's the mean, the X bar. Here's the standard error. Remember, the standard error is this entire denominator. The standard error is the standard deviation of the distribution of sample means. This value here is S. This is just S, just the S. And just to illustrate, let me show you that if I take the standard deviation and divide it by the square root of 15, which is the sample size, I will get the standard error. You don't have to do that because it's already done for you, but I just wanted to show it to you. So I can now use this information to calculate my test statistic. My test statistic is equal to, and I'm going to have to use parentheses if you know anything about the operations, mathematical operations. I'm going to have to put the mean minus, now this thing here, this mean sub 0, is the hypothesized mean, and that will always come from the null hypothesis. So that's 25, close the parentheses, divide by the standard error, and my test statistic turns out to be 2.693. What I need to do now is go get the critical region. Now this is a one-tailed test because we have a greater than, and not only is it a one-tailed test, it's a right-tailed test. How do I find the critical region? Well, the critical region is determined by the sign of the alternate hypothesis is greater than, and that's why I have a greater than down here, and the level of significance. So what I'm going to do is I'm going to go up here to formulas. I'm going to select more functions. I'm going to select statistical, and I'm going to run down and find the t distribution. And when you find the t distribution here, you see several things. One, you see a t distribution, but you also see a t inverse. So let me talk about that for just a minute. The difference between those two is this. If you know a probability and you want to find the random variable, in this case t, you use the inverse function. If you know the random variable t but want to find the probability, you use the distribution function. So in this particular case, I want to use the inverse function because I know the probability that I want, the 0.01. I want to find the t value. So I'm going to go down here and I'm going to use the t dot inverse. And now here's the thing about the t inverse function. the probability that it wants as an input here is always the left tail. Always the left tail. Well, this is a right tail test, so we want 0.01 in the right tail. Therefore, the left tail is whatever's left over, which would be 0.99. And then the degrees of freedom is n minus 1, the sample size minus 1, which in this case was 14. So we have a degrees of freedom of 14, and we have a critical region of 2.62449. Now let me say that again. In order to get that critical region, I use the inverse function. And in the case of the t inverse, it always assumes the left tail. So if you're doing a right tail test and you want, say, a 0.05 in the right tail, you would have 0.95 in the left tail. Okay? Now, the test statistic is 2.69. 2.69 is greater than 2.62. So the test statistic does fall in the critical region. So our conclusion is the number of patients that we handle per day is more than, I'm going to go down here, more than 25. We rejected the null hypothesis and accepted the alternate hypothesis, which is that the average number of patients that we can accommodate in a day is more than 25. Now let me just do one other thing here. I talked to you just a few minutes ago about p-values. So let's calculate the p-value here. P-value is based entirely on the test statistic. What you do is if the test statistic is positive in this case, the t-value is positive, you want to find out what's the what percentage of the t-values are greater than that. If it's negative, you want to find what percentage of all t-values are less than that. So to do that, since you know the t-value and you want the probability, you use the distribution function. So I'm going to go up here to Formulas, More Functions, Statistical, and I'm going to use the distribution function. And in this particular case, we do have a right tail. Now, notice up here you just have a t distribution. That gives you the left tail. You have a t distribution to tail, and you have a t distribution right tail. I'm going to select the t distribution right tail. And the t value is the test statistic, and the degrees of freedom is 14. So our p-value is 0.00874, which means that if we reject the null hypothesis, there's only about 8 in 1,000 chances that we would incorrectly reject. That's smaller than the 0.01 that we said at the onset of this test was acceptable as a risk. So based on the p-value, since p is smaller than alpha, we again reject the null hypothesis and reach the same conclusion. So based on either the comparing the test statistic to the critical region or the p-value to alpha, in either case we reach the same conclusion. Okay, now I want to look at a couple of examples where we compare the means of two populations. So we've got a couple of examples here that would be the standard way that the problem might be asked. One here, is there any difference in the average number of defects produced on the day and the afternoon shift at a particular production facilities? So since we're saying, is there any difference, that would be the null hypothesis would be equal, the alternate would be not equal. Or here's another, is there a difference, where you're talking about the number of days taken off by young workers versus older workers. And then finally another one where we look at the value of home appraisals by two different firms. So in each of those cases we have two populations, and we're looking at the mean of those two populations. So we have on Blackboard a probability and statistics formula sheet that I'm going to refer to in just a minute that gives you a lot more information about these tests, and you may want to refer to that when you have a question, but I'm going to refer to it in just a minute. So anyway, it's on Blackboard. Let's take a look at this example. We have a medical facility in the Myrtle Beach area. It's got two locations, one in Murrells Inlet, one in Little River, and the Quality Assurance Department wants to know whether there's any difference in the average waiting time for the patients at the two locations. Now there's a statement here that says, assume the population variances are not equal. I'm going to explain to you why that's in there in just a minute, but that is important. Okay, so let's actually go look at the data. So here's an Excel spreadsheet with the data. It turns out that if you want to do a hypothesis test on the mean of two different populations, there are 4 different possible test statistics. Notice how we've written our hypothesis here. We want to know if the average waiting time at the Little River site is any different than the average waiting time at the Murrells Inlet. So this is a two-sided test. So we're going to have a right tail and a left tail test both. We choose a level of significance of 0.05. And now we have to go find the test statistic. And there are 4 different test statistics that are appropriate when you want to test the means of 2 different populations. And we can find those on that formula sheet that I was just talking to you about a minute ago. Here's a decision tree that helps you with the decision. So the first question you ask anytime you know you are testing a hypothesis on the means of 2 populations, you need to walk through this decision tree. The first thing you ask yourself, are the samples paired? Now what in the world does that mean? Well, I'm going to show you what it means. This data, by the way, is not paired, but the next example I'm going to do in just a minute, so I'm going to skip over to it. This data is paired. Data is paired if a sample from each population is collected on a single entity, in this case, a family. So in this problem, which we're going to do in just a minute, we want to know whether one insurance company is cheaper than another. So it wouldn't make sense to, for example, pick one family that had 3 teenage drivers and see what the cost of their insurance was, and then another family that had 2 adult drivers and compare their cost, because it's just not a fair comparison. If you want to know whether Progressive is cheaper than Geico or not, you need to compare the 2 prices against the same family under the same coverage. So that's a paired test. When you take a data point from each population against a single entity, again in this case a family. So this data is paired. This data is not paired. We don't have anything that we're collecting the data on. That's one thing. The second thing is, if the data is paired, it has to have the same number of observations in each of the samples. This doesn't. Even if it does, though, that doesn't mean it's paired. You still have to be collecting the data on a single entity. So let's go back to our decision tree now. We now know that our data is not paired. So we go over here. Do we know the population variances? Well, no, we don't. All we have is the sample data. If we did know the population variances, it would be, the test statistic would be Z. But we don't. So the next question is, do we know whether or not we can assume that the population variances are equal? If we can assume they're equal, we have this t-test. If we assume they're not equal, we have this t-test. And if we go further into this formula sheet, you can actually find the formulas for how you calculate the t-value. I'm not going to do that right now because, in fact, Excel will do that for you. So let's go back and take a look at our data, our problem said that we could assume that the population variances are not equal. We knew that the data is not paired. We know that we don't know the population variances. All we have is the sample variances, and the problem description told us to assume that they're not equal. So we're going to use a t-test assuming unequal variances. This is how you calculate the t-value right here. This is the formula for calculating the t-value. You take the mean of sample 1 minus the mean of sample 2 minus any assumed difference, which in most cases is 0. If I were to say, for example, that we think that the average waiting time at Murrells Inlet is 5 minutes longer than the average waiting time at Little River, then this would be 5. But we didn't say that, so this number is 0. And these are the sample standard deviations down here. This is the formula for calculating the degrees of freedom. So this looks a little bit cumbersome, and in fact it is a little bit cumbersome, but the nice thing about it is that Excel will do this work for us. So I'm going to go to data. I'm going to go back to my data analysis that we looked at earlier. And I'm going to go clear down to the bottom. And down here we have 4 different t-tests. The 4 tests that I just showed you a minute ago. The t-test for paired data, the t-test for data that's not paired and the population variances are not known and they are assumed equal, or not known and assumed unequal, or the last one, the z-test, when the population variances are known. In our particular case, we want to use the t-test assuming unequal variances. So I select that, hit OK, and I start getting my data. Doesn't matter which one you call 1. I'm going to let Little River be 1. And then I'm going to let Murrells Inlet be sample 2. The hypothesized mean difference, as I just discussed a minute ago, is 0. We do have labels. The level of significance is 0.05. And again, when I click output, for some reason the cursor jumps up to the input, so I've got to bring it back down, and then I've got to select a place to put my data. I hit OK, and lo and behold, Excel's done all this work for me. It's calculated the t-stat using this formula right here. It's calculated the standard, the degrees of freedom using this formula. It's calculated the standard deviations and means, sample means, and so on. So the test statistic is equal to minus 1.1. The critical region, we have both a right tail and a left tail. This is a two-tailed test. So down here's the critical value for a two-tailed test. That's the right side. So we have equals the 2.144, and the left side would be equal to minus 2.144. It's nice that Excel did all this work for us. Now all we have to do is write our conclusion. Minus 1.1 is not bigger than 2.1, nor is it smaller than minus 2.1. So our conclusion is that we do not reject the null hypothesis, and we conclude that there is no reason to believe, that the average waiting time is any different at the 2 locations. Let me pull this back over here. Okay, now fortunately for us, we don't have to calculate the p-value either. The p-value for the t-tail test is given here, so our p-value is equal to 0.2879, which is much bigger than 0.05. So if we were to reject the null hypothesis, there would be almost a 29% chance that we incorrectly rejected. We started this hypothesis test saying we only were willing to live with a 5% chance of incorrectly rejecting. A 28% is unacceptable, so we will not reject, and we reached the same conclusion. Okay, so that was a hypothesis test comparing the means of two populations where the data is not paired, the population variances are not known, and so we have to use the sample variances, and they're assumed to be unequal. The population variances are assumed to be unequal. Okay, our next example, we're going to look at the problem we just looked at a few minutes ago, the insurance problem, where we want to know if there's any difference in the rates charged by two different companies, Progressive and Geico. As I mentioned before, it wouldn't make sense to do anything other than compare the prices on the same family. So this data is paired. We're going to use a 10% level of significance in this case, and we want to know, is there any difference? So again, we have that equal versus not equal hypothesis. Okay, so here's my data. We can go back. We know we're comparing the means of two populations. The first thing we ask, is the data paired? It is. So we're going to use the paired test. So just remember that the test statistic is different. That's basically, the test statistic is really the only thing that's different for all these different tests, is how you calculate the test statistic. And it basically depends on how many populations you're checking or testing and what the parameter is. In this case, we're comparing the mean of two populations. The data is paired. This is the t-value. And if you'll notice, this is a different t-value than we did in the last one. It's a different test. It's still t, but it's a different t. It's calculated differently. We don't have to worry about that because I'm going to go back to data analysis. This time I'm going to pick the t-test for paired data. And it asked me for the first sample, and I'm going to choose Progressive. The second sample, and by the way, it doesn't matter which one you call first and which one you call second. Again, the hypothesized mean difference is 0. We do have labels. In this case, I'm using a level of significance of 10%, so I want 0.10. And now I've got to find a place to put the output. Again, it jumped up to the input. Don't know why, but I got to bring it back down, and I will put my output right there. And Excel has graciously done all my work for me. Oops, going down a little too far. The test statistic is minus 1.7. The critical region for a two-tailed test is, the right tail is 1.76. The left tail is minus 1.76. Our test statistic 1.74 is not bigger than 1.76, and it's almost as small, but it's not smaller than 1.76. So our conclusion is there is no difference in the rates of the two companies. There's no difference in the rates. Let's go look at the p-value, see if it gives us the same conclusion. It better. The p-value for a two-tailed test is 10.3 equals this p-value, just slightly bigger than 0.10, just slightly bigger. But if the p-value is bigger than alpha, you do not reject, so we would conclude that there is no difference in the rates. So there's a couple of examples of hypothesis test, and the key thing you need to remember is that hypothesis testing is basically a cookie cutter type deal, but the main thing is, how do you get the test statistic? And that essentially depends on how many populations you're testing and what the parameter you're testing is. So what we've learned, We wanted to talk about hypothesis testing. We understood that we had to know something about sampling distributions, and how important that central limit theorem was, because without that central limit theorem, we couldn't be using the normal distribution to do all these probability calculations, and we'd be in trouble if we couldn't do that. Central limit theorem was critical. We learned about type 1 and type 2 errors, and then we learned about a p-value, very important concept, the p-value. And finally, I did a couple example hypothesis tests for you. I hope you understood what I did. If not, we can talk about it when you do your virtual office hours or virtual classes.